recently built a plugin, it's called the Isight for Abaqus plugin, which essentially exposes a subset of Isight functionality, but inside your Abaqus CAE sessions. And it allows users, Abaqus users, to run design studies on their existing Abaqus CAE models. And this plugin is available free of cost for you. Once installed, this plugin appears as an additional tab inside CAE. So you can see you have a model tab, a results tab, and once you install the plugin, you have a new Isight tab. It exposes a subset of Isight's exploration functionality like DOE and optimization inside your Abaqus CAE sessions. It has a very easy to use wizard-based setup that guides the user to define their exploration, formulate their problem using your available Abaqus model parameters, and then you can execute your multiple Abaqus runs either locally on your machine or also via an Hpc configuration. So this plugin is available free of cost and can be downloaded from the Simulia learning community. All that you need to do here is go to this page and download the plugin files. And to start using the plugin, just like with any other Abaqus CAE plugin, just take these plugin files, dump them in your Abaqus plugins folder in the installation directory, and it's ready to use. So now I want to take you through a quick demonstration of using this plugin. So I will go to my Abaqus CAE session here. It's a very simple model that I've set up. I have a cylindrical block of soft material. It's a high-perform material, and I have a hemispherical indenter here. And I want to analyze, I want to run some repetitive studies on this model here. I want to analyze the effect of the velocity of this indenter, as well as the radius of the hemispherical punch here. How does that affect the stress state in my soft material here? And in order to analyze that, I now have my Isight plugin. So I can quickly launch my plugin inside my CAE session, and that connects to Isight, and it exposes that functionality inside my CAE session. So it starts reading my CAE file and my output database file, and then it lets me perform these design exploration studies inside CAE. So for instance, if I want to run a design of experiments on this model, let's say I want to run 10 different iterations, and in those 10 different iterations I want to vary some inputs and monitor the effect of varying those inputs on certain outputs. So you can see that this plugin has read all my Abaqus model parameters, and like I said, I want to vary my velocity boundary condition, and I can specify what my lower bound is for my velocity, what my upper bound is right here, if radius of the indenter within certain bounds. So I can also specify that information here, kind of defining my design space. If there's anything else that I want to change, for instance, if I want to evaluate the effect of friction, I can also do that. So you can see friction properties are included in my model parameters here. I can specify how I want to vary my friction. So this is essentially defining my input design space. So what are the input parameters I want to vary? You can see that they, the green dot here indicates that they are active inputs in my DOE formulation. And the next thing I want to do is define my outputs. So what are the outputs that I want to monitor the effect on? And your CAE file may have a lot of outputs, so you have a very useful filter function here. So if I want to look at my von Mises stresses, so I'll just go ahead and select the maximum magnitude of my von Mises stresses. For instance, if I have to monitor the reaction force on my indenter, I'll also, use a filter function to select that reaction force really quick. And once I'm done with selecting my outputs for the study, this is all the configuration that we needed to do. So select my inputs, specify bounds, then select my outputs, and then I am ready to run this plugin for the DOE setup for 10 different iterations inside of Isight. So as soon as it accepts these outputs here, we will be ready to run our Isight for Abaqus plugin here. So you can see that the last step here is reviewing and running my design model. You can see this is my Abaqus job submission command. If I want, if I'm running a long-running simulation, I can also add a CPU's argument and add the number of cores that I want to run my job on. It tells me what DOE technique I'm using. I have 3 active inputs, 2 active outputs. These are the number of DOE iterations that Isight will be running for me. And in case you want to set up an Hpc configuration, you can also do that here. So for instance, if you want, you've set up everything on your local machine, but you want these jobs to run on a remote cluster, you can use any of these queuing systems to submit your job on the remote Hpc cluster. And finally, you can just give give a certain name to your job. So for example, we say indenter force as the name for the job. And then that's the entire setup here. We are ready to run the model. As soon as I hit run, it's going to open up runtime gateway. That's where the Isight models execute. So the entire process of setting up the model was done inside of Abaqus CAE. So you didn't have to learn a new tool in order to set up your model. All that setup was done inside of Abaqus CAE. So you can see to save us some time here, I have already run this model for 10 different DOE iterations. So it gives me, it's varying my friction values, the radius of the indenter, as well as the velocity of the indenter, and it's trying to evaluate the effect of that on the reaction force, the maximum magnitude of reaction force on the indenter and my von Mises stresses. So it gives me results in a tabular format, but what's really interesting is it also gives me a result in a more graphical way so that I can understand by looking at correlation table. Now this is essentially a heat map of linear correlation values between my inputs, which are here, and my outputs, which are on the y-axis here. And by looking at these values, now the higher the values, these correlations are essentially ranked from -1 to +1. If the value is closer to 1, it means there's a strong correlation between my input and output pair. And if the value is closer to 0, it means that's a weak correlation. That input and output pair is not so highly correlated. And the sign here indicates whether it's a negative relation or it's a positive relation. Now you can see, if you look at this correlation map, you can see that your von Mises stresses are highly correlated to your boundary condition. So your velocity boundary condition that you've applied, it has a strong correlation with our von Mises stresses as well as our reaction force. But on the other hand, if you look at, this is our friction values, the friction is not so correlated with our outputs in this study. So this kind of helps you understand those relations here. We also have a number of scatter plots. So if you want to look at your points and what the scatter of that looks like, what's the Isight also gives you a fit. So it tells you what the fit looks like, what's the goodness of the fit. So it tells you what the R-square value is, so that you can look at what the relationship between your inputs and outputs are. You can create graphs for yourself. So if I want to create something like a Pareto graph, now I want to, Pareto graphs essentially rank the influence of your inputs on your outputs, and it tells you which is the most influential parameter for a certain output. Now if I do that for my von Mises stresses, I can immediately see, let me pop this graph out. Now you can see it gives you a percentage effect on the maximum magnitude of von Mises stresses, and it tells me that my velocity boundary condition is the most influential parameter for my von Mises stresses. And the next one here is friction, but it's in close competition with the radius of the indenter. And the color here indicates, if you see a blue color, it indicates a positive effect. If you see a red, it means there's an inverse relationship. So these are the kind of post-processing that you can do. You're not just limited to that, but if you run a DOE, you can quickly create a surrogate model, or what we call as approximation model on your data, and then you can look at the response surface. How does the response surface look for that certain set of data. And Isight will also give you the slider bars. So essentially, you can slide these bars and see how it changes your response surface when you move the bar within your bounds. So this is just some post-processing that you can do in Isight. A lot of it is pre-configured for you in the data analysis tab. You don't have to do anything. You just have to come here to see the plots, but then you can also create additional graphs if you wanted to. So that was a quick demonstration on the plugin as well as some post-processing capabilities in Isight.